Okay, let's begin. Today I want to share this, this paper named Towards Practical Multi-Object Manipulation Use Relational Reinforcement Learning from Richard Lee and other authors. And I will share this paper from introduction, background, method, result, and also the discussions. First is the introduction. This paper is trying to develop a data efficient algorithm that can learn from the spare reward. So it try to use the curriculum learning to pace the agent's learning. But with the curriculum learning, they need some good inductive bias. So they try to add some relational inductive bias. So that's so finally they try to use attention-based graph neural network as a policy associate with the curriculum learning in the multiple objects manipulation task. And about the background, first is related to the relational inductive bias. As we all know, in the deep learning area, there are lots of layers. So different layers will have different inductive bias. For example, for the full connected layers, the entity is the unit, so the relations is O to O. In this way, the relational inductive bias is very weak. So for the convolutional layers, they focus on the spatial translation. And for the recurring layers, they focus on the time translation. So for the graph neural network, they will pay more attention to the node and the edges. So they will have a very strong relational inductive bias. And the invariance is the node and the edge information. This picture is come from the reference one. So if someone want to learn more detail about this, can read this this paper. And about the curriculum learning, the curriculum learning is trying to train models in a meaningful order, which means from the easy to the harder ones, so that it can get more sample efficient and efficient learning, and also avoidance of the local minima. There are also another, I think it's good paper for the curriculum learning. It's also a survey. And about this method, we can see here, this is the final performance of this paper, and it tried to stack some blocks. And the method, they use relational reinforcement learning. So as observations is the gripper feature, block feature, and also the goal. The reward is a sparse reward, so it only gets some reward after they complete some important step. So they will got one when this is the location of the block, and this is the goal location, this is the goal position. So if one of the block is close to the goal position or in the goal position, it can get one reward. But there are also some bugs. So the second part is for debug for this method, because sometimes the gripper just hold the block and do not put it into the goal position. So they need this try to subscript this part to debug this problem. And during the train step, there are three kind of tasks. One named directly means the robot was directly tasked to learn a policy to stack 6 blocks start from the crash. And the second one named uniform means at every episode, the number of the block was uniformed, sampled from between 1 to 6. And the final one is the sequential, which means that after the robot prefect stack n steps 1 blocks, and then it was given n blocks to stack. Actually, the sequential one is the final method which this paper try to use. And this is the result. We can see that with the curriculum learning, the robot can stack more than 5 blocks. And without the curriculum learning, the performance is not very well. And after the training, they also evaluate this method or this trained policy to another target task, means that they will try to stack in one single tower, or target task 2 is try to build a multiple tower, and the third is try to build a pyramid. So we can see that green one, we can see that it can work well, although they never trained for the pyramid shape. And did I present too quickly? And the discussion for this method, finally, they still need 35 workers and even several days to train it. And also, it only tests on the blocks, which means that they never test it on some objects with some complex shape. And also for the future direction, first, because in this paper, with the curriculum learning, the curricula is try to increase the number of the objects or the blocks which you need to stack. So they will try to find some automatically curricular design. And also we can see that it still needs many workers and many times and also memories to train the policy. So the third possible direction is try to find some computationally efficient method. And also they use the state as input. From the state is directly from the simulator. So maybe we can use some visual or other sensory observation. I think that's all. Is that too short?
Thank you. Is there any questions?
Yeah, thanks for the presentation. So what is the state observation that they're using right now?
Wait a moment. This observation is the gripper feature, means the position of the gripper, and also the position of the blocks, position and the angle and the orientation, and also some speed of the block. And about the goal is just some position. goal position.
And I believe that the goal positions are fixed during the training, right?
Yeah.
Mm-hmm.
And also for every block, the goal is sample from the goal distribution, because we want to manipulate 6 blocks, so it actually will have 6 goal position, and for each blocks it will sample from this 6 position.
So the goal positions are fixed, but like the color, like which block should go to which goal block is changed, right?
Yeah.
Okay, yeah. Yeah. And you only have in this reward function only one term work for the grip away. Is that right?
Yeah.
Mm-hmm. Yeah.
Any other questions? Okay, can you go to the slide 8?
Yes. This one?
Yeah, this video.
Excuse me, since you two are in the same room, your voice has like feedback, so one of you should mute the mic while the other is speaking.
Okay.
Okay. I use hands-free for this purpose, I know, but maybe it's not helpful. So why is it I see the echo?
I try to mute my mic.
Okay. So why is the drop in the performance of this method after learning to put one block? The green line.
You mean this part?
Yes, yes.
Actually, I don't know, but yeah, they didn't see this detail in the paper.
So I think it's because of the curriculum learning, because after it learns the task, it changed the reward functions or dynamics. So in curriculum learning, there are usually some drops. And another question, you said that for the training, even when they have certified workers, it takes several days to train. Why is that? Because the number of samples are high, or because the training of in graph neural networks is computationally expensive, or any other reasons?
Actually, this paper already make the computation more efficient, but it still need much. They say something about the memory, so I can show that in the wait a moment. Can you see this paper? Yeah, actually I think the memory requirement and also the time requirement it's come from the spare reward, because you only give the reward for after they complete or finish some important step, right? So actually you need lots of times and also memories to do some exploration, and so that to fix this problem, this paper tried to use the curriculum learning, and they cut the memories, I think. Can compared to another without the curriculum learning, but it still needs memories and computations and time.
So one question.
Try to go back to the slide.
So one question is that in recent papers, they use massive parallel environments to make the training time much less. Is it possible in this scenario or no? I mean, in this experiment and in this method, can they parallelize the environments massively, or it's not possible?
You mean make them? I'm not very sure about that. What do you mean parallel?
So right now they have 35 workers. If we increase the number of the workers, does the training time reduce or?
Oh, I think it will works, but I think the memories still need.
Is there any other questions? Okay, everyone, thanks for attending this session. I hope you have a nice holiday. If anyone wants to present a paper in these events, they can contact me. Thank you, everyone. See you in 2 weeks. Bye.
Thank you. Bye.